Okay, here we go. The last of the vector videos. Applications of vectors. So, those of you who are taking physics, this will make a lot of sense to you. For those of you who are going to take physics, and everybody should because it's really awesome and cool, this will make sense to you later. And I should say this will help you out. The wind is blowing at 20 miles per hour in the direction of 330 degrees. Express its velocity as a vector of I in terms of J. So first of all, you have to understand what they mean by the direction of 330 degrees. You can decide where your direction is coming from. For us, to make my life easy, I'm taking it from the horizontal, so 330 degrees gives us a vector here. So that's my 330 degrees, and that's our magnitude. That's very easy to convert it to terms of I and J. A equals 20 times the cosine of 330 degrees. B is equal to 20 times the sine of 330 degrees, and that gives us the vector of, sorry, we want it in IJ form, 10 root 3 I minus 10J, or 17.32 I minus 10J. Piece of cake. That's the easy one. Okay, resultant force. A resultant force is the sum of all the forces acting on an object. So basically, you take all the forces, convert them to vectors, so you have magnitude and direction of the force, combine them together, you add all of those vector forces together, and the sum of them gives you what is actually happening to the object. So think about a tug of war. If you have one side pulling with one force, one side pulling with the other force, the way the flag moves in the middle is the resultant vector of the forces. Okay, that's what that is. And you can describe most motions and so many things in physics can easily be described this way. So, an object at the origin is acted upon by two forces. A 150-pound force makes an angle of 20 degrees with the positive x-axis, while another force of 100 pounds is at 70 degrees. Find the direction magnitude of the resultant force. In other words, what is moving the object? What direction is it going? What is the combined forces? So we have one force that is going 150 pounds at 20 degrees. And we have another force that is 100 pounds at 70 degrees. What is the resultant force? So basically what you have to do is you have to convert these two angles themselves into some other form. Instead of magnitude and direction, you need to convert them into I or J or something else. I and J are the easiest ones. So we have 150 cosine 20 degrees times I plus 150 sine of 20 degrees J plus, and do the other vector, 100 cosine of 70 degrees I plus 100 sine of 70 degrees J. And if you convert those over and add them together, your resulting vector would be 175.16 I plus 145.27 J. So that's our resulting vector. However, we want to put this in the magnitude and form that we were originally given. So our magnitude would be 175.16 squared plus 145.27 squared, and you take this, add them together and take the square root, and you get a resultant force of 227.56 pounds. And then you have to figure out the direction. Theta is equal to the inverse tangent of 145.27 over 175.16. And you end up getting theta is a 39.67 degree angle. So we're looking somewhere in here like that. That's our resulting one. And if we take the other two vectors and add them together, it makes sense. So what is our force pulling on this? We have a 227-pound force at an angle of 39.7 degrees. Here is a extremely typical physics problem. Okay, you have a box, you have something on a ramp. We have to figure out all kinds of things. There are lots of different forces that we can discuss in this problem. We can talk about friction, talk about gravity, talk about all kinds of stuff. So a 200-pound box lies on a ramp that makes an angle of 24 degrees with the horizontal. A rope is tied to the box from a post at the top of the ramp to keep it in position. Ignoring friction, how much force is being exerted on the rope by the box? Okay, so in other words, what is this force here? So what we can do is we say, all right, we have a component vector. We have a 200-pound force. 200 pounds is going straight down. This is broken down into what's pushing it down the force, what's pushing against the ramp in this direction. We call this our y, we call this our x. We have our force, we have our x and our y. This is actually a really easy one. X is the force times the cosine of the angle that we have the ramp. Now, we don't use the 24 degrees. We end up using 24 degrees as this angle here. This is the angle we want. If you think about that as being a right angle, this ends up being 66 degrees. That's why we are using 66 degrees. And the force we are finding is 81.35 pounds. So we have 85 pounds being pulled on the rope. Let's hope the rope is strong enough to hold 85 pounds. It's not one of those Acme ropes that the Roadrunner gets. See, I can still tell jokes even if nobody's here. The airplane is traveling at 50 degrees an airspeed of 300 miles an hour. There's a 35-mile wind coming from 120 degrees. What is the course and ground speed of the plane? In other words, the resulting vector of the two planes. Now, we have to set up our vector form. We have to get our standard. Generally speaking, when we're talking about traveling with this, we are measuring clockwise from north. So we set up an XY system and we're traveling at 50 degrees with an airspeed of 300 miles an hour. So we start here is due north. So we want to come 50 degrees off of that. And that's the result. That's the vector of the plane that we have. Okay, it's 300 miles an hour at 50 degrees. We have the wind is at 120 degrees. So the wind's 120 degrees is over here somewhere, blowing out this way at 35 miles per hour. We want to know the resulting vector of the two of them. Obviously, these are not scale if that's 300 and this is 35. I really don't care. What we need to do is convert them from magnitude and direction into something else. So the plane P is 300 cosine of 50 degrees I plus 300 sine 50 degrees J. So the vector for the plane ends up being 192.84 I plus 229.81 J. And then we do the same thing for the wind. What is the color of my wind? There we go. 35 cosine of 120 degrees plus 35 sine, it's 120 degrees I, let's get that I in there, 120 degrees J. So our wind in component form is, excuse me, negative 17.5 I plus 30.31 J. And the resulting vector, if you add the two of them together, the ground speed is 175.34 I plus 260.12 J. That's the resulting vector. So the plane is, let's see, find the magnitude of that. 175.34 squared plus 260.12 squared is equal to 313.7 miles per hour. So that's the ground speed, the equivalent ground speed. So it's actually traveling faster than it is because it's being pushed a little bit. However, it's not being pushed on its direct course. The angle it's at is the inverse tangent of 260.12 over 175.34, and we get an angle of 56.02 degrees. So it's off by 6 degrees, but moving faster than it was trying to. Easy peasy. Ooh, we got a car. Find the magnitude of the force required to keep a 3,500-pound car from sliding downhill inclined at 5.5 degrees from the horizontal. Find the magnitude of the force against the car against the hill. This is actually really easy. So this is the X force we want. That is the force pushing down on the car that way. We want the Y force. That is the force going down. What is the force that we actually have? We have 3,500 pounds pushing down. We want to break that into its components. Once again, if we set this up, that's 5.5 degrees here. That would make this 84.50 degrees there. So for part A, X is equal to 3,500 times the cosine of 84.5. So the force pushing down is 335.5 pounds. So the brakes are holding it. Let's see, it's the brakes are holding it. There's 335 pounds of force against the brakes. And then for the Y coordinate, the amount pushing against the hill, Y is equal to 3,500 times the sine of 84.5. And we have pushing against the hill, 83.9 pounds pushing against the hill. Break it down into its parts. All right. Okay, so a river flows from east to west. A swimmer on the south bank wants to swim to a point directly north of her starting point. She can swim 2.8 miles per hour. There's a 1 mile per hour current. Okay, at what direction should she swim in relation to the south bank? So here's the deal. She wants to go to there. She needs to swim at an angle here because the water is pushing against her there. Okay, so here's what we need to do. We need to figure out what our angle is. That's all we need to do. We don't need to figure out anything else. Okay, what angle should she be at? So we just need to set this up. So this is a 1 mile per hour force here. And this is how fast can she swim? She can swim at 2.8 miles per hour. So we just set it up and we're looking for this angle right in here. So let's set up a triangle. We want this angle here. This is 2.8 and this is 1. What's my angle? So I set up, okay, theta is equal to opposite over adjacent. Inverse theta equals the inverse sine of 1 over 2.8. And we get an angle of 20.92 degrees. However, this angle in here is 20.92 degrees. But what is the question actually asking for? What direction should he swim in relation to the south bank? So it's actually asking for this angle here. That's easy. 90 minus 20.92. And she should swim at an angle of 69.08 degrees. So basically 69 degrees from the bank is the angle she should swim at if she wants to get directly across. So you swim at a little bit of an angle, and the current will push you down, and she should land directly across. All right.